वीडियो தெரியுதா? ஆடியோ கிளியரா இருக்கா? இத்தனா இத்தனை ஸ்டார்ட் பண்ணலாமா? குட் மார்னிங்.
மேம் வீடியோ தெரியல மேம்.
வீடியோ தெரியலையா? இப்ப
ஸ்டார்ட் பண்ணலாம் மேம்.
ஸ்டார்ட் பண்ணலாமா? ஓகேங்க சார், தேங்க்யூ. Good morning, everyone. I am Dr. M. Subhatra, Professor and Head, Department of Electronics and Communication Engineering, VLSI Design and Technology. On behalf of RMK Group of Institutions, I am delighted to welcome you all for the today's session on Generic Talk Series. It is my pleasure to introduce our distinguished speaker, Dr. M. Deepak, Senior Lead Scientist in Earth Observation at Kroppen, Bangalore. Dr. Deepak Murugan holds a PhD from Indian Institute of Technology, Roorkee, and a master's degree from Linköping University, Sweden. He has more than 10 years of experience in remote sensing, Earth observation, geospatial analytics, computer vision, and machine learning. His work focuses on applying advanced technologies to solve real-world agricultural and environmental challenges. Over the past decade, he has developed scalable systems for deforestation monitoring, crop health advisory, crop identification, and smart irrigation scheduling. His expertise in including satellite images, geospatial intelligence, computer vision, and machine learning makes his work highly relevant to emerging field of precision agriculture and sustainable resource management. We are privileged to have you to share your knowledge and professional insights with us today, sir. On behalf of RMK Group of Institutions, I extend a warm welcome to you. We look forward to an informative and inspiring session. Over to you, sir.
Thank you, ma'am. Thank you for the introduction. So, be glad to give a talk on the precision agriculture and remote sensing. Is my video visible? Okay. Yeah. So, let me share my screen. I hope my presentation is visible.
Yes, it's visible.
Okay. Good morning, everyone. Today we are going to talk about something that touches almost every family in this country, which is farming. But only difference is we are going to look it from a different angle, which is not how we do uh, by visiting a farm, but we are going to look it from the sky, right? And I will also show how satellites, drones, and AI tech is completely revolutionizing the entire agri-tech space. And using all these techs is not far-fetched from reality, but it is really happening these days. And since there is a lot of things happening, there is a lot of opportunity for people like you to jump in and have a head of that. And what we will cover today is first is we'll talk about the different challenges that persist in the agriculture space, and then how remote sensing is trying to help that. And we'll also be talking about the modeling approaches, physical and AI models, and then the interesting part, the most interesting part, next frontiers, and which includes drone, AI, smart glasses, farm robots, and whatnot, right? This is what we're going to cover today. So the main problem with agriculture is the techs are not used at like high level in India, and when the techs are useless if you're not trying to solve the real problem which agriculture faces, right? So there are almost like 146 millions of land holdings. Meaning in India there are 146 around 146 millions of land holdings, and Average landholding size is around 1 hectare, and out of that, like 86% are having an area less than 2 hectares, which is quite small compared to in US. The average landholding is almost like 20-30 hectares, right? And what happens is like each farm has to be monitored, and decision has to be made on a daily basis, like irrigation, fertilization, and other things, right? And 146 millions of farmers are going to do decision on daily basis, which is a huge uh, amount of decision making that is happening. And almost like 50% of Indian workforce is dependent on agriculture. So first we look at what are the problems we face in agriculture. Like as I said, the farm holdings are fragmented, meaning the plot size is pretty small, and field level monitoring has to happen, and it's quite a tremendous effort there. And then second one is the water problem. So due to erratic monsoon and depletion in groundwater, right? So irrigation is still mostly done at guesswork, and there is not enough water. And even now we can see due to delayed monsoon, there are delayed sowing of paddy across India. So the other challenge which we see is the use of fertilizers and pesticide. First, fertilizer and pesticide are used as a blanket spray, right? Maybe not the entire farm requires so much of fertilizer or pesticide. Maybe a part of the farm only is affected, and we are supposed to apply it in the part of the farm. But instead, people tend to fertilize and apply pesticide across the field. And then there is persistent yield gap, which means whatever yield is being produced at a farm is far less than what it can produce altogether. And there is a challenge on post-harvest loss, and there is no real-time visibility of any of these being monitored, right? So so what farmers see is like this. These are all not old problems. This is like these are all old problems, and this is not yet solved. And everyone knows there is this problem. Like farmers, how do they do? They go to the farm, they visit their farm, and they judge by seeing what is happening. So before visible damage is there, the plant or the crop is already damaged from within, right? And what does a farmer do when there's a damage? So first he uses his own experience, or maybe he talks to a neighbor, and with the availability of internet search or YouTube, right? People nowadays check if there is any solution available, and whatever solution persists, they try to replicate that. But it is not the most right way to do, because uh, whatever solution you get, it is more generic than specific to his farm, right? And maybe you can ask some extension officer or agronomist to come and visit. Maybe they visit once or twice a whole crop growing season. So it is not very feasible for a farmer to do. And in system level, like at a country level or a state level, what how do the agriculture department, how do they do? They send surveyors to collect small samples across different regions. It's impossible to collect every every farms in the whole region, right? So they send surveyors to collect small samples, and then that small samples are then generalized for the entire region. And even these reportings are all delayed, and whatever we get as a information is almost at the end of the cropping season, right? So what is the solution for this? So instead of having farmers or surveyors visit the field very often, so we can use the satellites. Satellites are revolving around the Earth 24/7. They can capture every part of the Earth, right? Every farm without having a difference in measurement or anything. So they can go around every farm. The whole country can be covered in within 5 days, right? So in 5 days interval, the whole country can be measured, and the same measurement can be used for say analyzing your farm, and then based on that give a insight. So you can consider this as a pipeline where the sensor can be satellite, it can be other sensors, which is in-field farm sensors, or even a drone or whatnot, like it can be a smart glass or robots, right? So what it can do is collect data and then give it to and you can pool it into a data layer. And once you have a data layer, and it can be passed on to a AI model which analyzes the data and then tries to find a correlation or events that are happening within the farm, and that can be then translated to a farmer as an insight. So it can be on his own language, it can be as a SMS, it can be as a audio message, right? So all this can be integrated into using technology, and if the last part is not being full-fledged by the technology, the whole technology is useless. So our focus is mainly on the farmer insight, right, rather than the data collection and other things. So first we'll start with what imaging, the remote sensing imaging is. So there'll be no much technical, it will be a very simple terms of imaging, right? So what is remote sensing, right? Remote sensing is nothing but you measure something without touching it, right? Instead of going and seeing, like touching and seeing, or feeling and seeing, it's more about standing far away and then trying to record the information. So in remote sensing, there are two types of sensing, which is passive and active. Passive is something like you use the sun light as a energy, and then whatever is reflected from the earth is being captured as a photograph or image. So it does not. It's like our normal RGB cameras which we use on a daily basis, right? And active sensing is nothing but we don't rely on the sun source. Instead, we have our own energy. We transmit the energy. We receive the reflected energy, and uh, it can help us in imaging throughout any time of the day, because sun is only available during the day, and it needs clear sky. If there is cloud, there is going to be obstruction. But in the active part, we just transmit electromagnetic signals, and then whatever is returned back is recorded as image. It's like a radar which people use in the airports for tracking the planes, right? So similar to that. So first is the optical remote sensing, where satellite actually captures the optical satellite actually captures RGB images along with other end of the spectrum, which is the near infrared. So near infrared contains a lot of information, which is more meaningful for a plant, to observe a plant, right? So the above one, what you see is a true color image. It's like similar RGB photograph which we take. So this is how the satellite sees this. And while we see in near infrared actually is a key indicator of how healthy your plant is. Like when the near infrared segment is reflecting, like when the vegetation is reflecting a lot of near infrared spectrum, it means the plant is very healthy. And if the reflection from the near infrared is less, meaning the area is like bare soil, or it can be a stress crop, right? And there are other indices, which is EVI, and based on this near infrared and red, we can compute index called NDVI, which actually gives the vegetation vigor or greenness. And the below one is the NDVI for the above image. Like I have computed the NDVI for the same date, right? And this is a region in Iowa. And EVI is similar to NDVI, but it has when the NDVI tends to saturate in certain timestamp, so that's when we have to use EVI, which is an enhanced index. And then if you want to know about the leaf and surface water content, right, like the wetness and other things, that there is an index called NDWI, which helps in seeing that. So how satellite sees from us, like apart from us, like this is how we see, right? We see the RGBs, and if I try to make a uh, image how satellite sees, it's kind of an analogy, I would say. Like this is not exactly how it's say, but it's if we have to visualize how a satellite sees, this is how it will be. So more red meaning more healthy or more dense vegetation is happening around this region, right? So you can see there are a lot of different reds, right? Like certain reds are mild, certain are dark, and you can see the bare soil in a different color. So this is how the satellite sees. And the main drawback of this optical is like when there is uh, cloud cover, there is the satellite doesn't see. The satellite actually has to see how like what reflection is coming from the sunlight, right? Like sunlight goes to the earth and it bounces back. So when there is cloud, none of the signal is actually passing through the cloud because it's a visible light, and then whatever uh, is uh, is reflected back. If there is a cloud, the satellite sees only the cloud, and generally our cropping happens around this monsoon season, right? In India, monsoon season is when like it's around June to October, and that is the main crop growing season. And in India is like mostly rain-fed irrigation, where we are more reliant on rain for our agriculture practices. So it's a common problem we see in India that when we need to actually analyze the crop, we see a lot of clouds, and we sometimes miss out on like 1 or 2 months of data is not available for us to even analyze. So what is the solution for that, right? So that is where this radar comes in. So radar, what it can do, it's that it can see through cloud, and it is not affected by cloud, and it can image around throughout the day. Like you can do it in the night or daytime, because it sends its own um, illumination, right? It tries to it sends the radar signal, and whatever bounces back is actually recorded as an image. So this is a sample radar image of the same region which you have seen the previous, almost in the same time window is also same. So and radar is sensitive to the vegetation structure as well as the underlying soil moisture in the soil. So these two information are more critical, and we get an additional level of information apart from what we see in optical, right? So these even though this looks more noisy, it's not as smooth as we saw in optical, but this carries a lot of valuable information within the so what, how do we choose, like what do we use? So signal source, one is the optical is uh, reflected sunlight, and the radar is like the microwaves which are sent and received back. And when there is cloud, optical is of no use, and radar can image throughout, right? And day and night capability, so more revisits are there, like we can do it even in the night, so we have more time to capture the images. And and it is mainly like optical is more suitable for crop types, stresses, indices, spectral indices, where radar doesn't have that capability, but it is able to have the analysis of the structure, and it can do the flooding. And the monsoon reliability is very low in optical, and radar is like you can rely even in monsoon season, right? So in throughout the monsoon season, the radar data is able to see through the clouds and record the information. So how do we choose, right? Which one to choose? We shouldn't go by either one of them. It's best use is like when we use it together. How do we use it? What are the data available in Indian context is like we have like most of these data are freely available, like the for agriculture at higher resolution, right? We generally go for the Sentinel, the two Sentinels, which is the passive one, which is Sentinel-2, and the active one, which is Sentinel-1. The Sentinel-2 is available at 5-day revisit, and the Sentinel-1 is like available at 12-day interval, and yeah, both are provided by ESA. And there is the NASA provided satellite, which is Landsat 8 and 9. All these three are freely available, and anyone who wants to look into, like interested in to look into data, they can just start with the Sentinel-2, because there is humongous tutorial available to get started. And you can download for your region. You can see how your region looks like and analyze, right? And then comes the NISAR. NISAR is the interesting program actually. It is NASA ISRO's joint mission, and they are yet to give their product in a full-fledged matter, but it has started recording the data, and they are calibrating their data, and soon you will get to see this NASA ISRO data. The interesting part is like it is a combination of L and S band, which is two different band, and they cover entire Earth in every 12 days. And then the last one is the PlanetScope. It's a upcoming, or you can say emerging technology, where it's a private player, but they cover entire globe on a daily basis, and they give data at very much higher resolution compared to all of these, which is 3 meters, and you can literally see very small land parcels very clearly in this. And then we have the images now. We have seen about the images and how to use this image. What do you get from this image, right? So the next part, which is coming to the modeling part. So first we'll talk about the like there are two types of model. One is the normal semi-physical modeling. The other one is the AI model. So we'll start with the semi-physical model. So in semi-physical model, like when we talk about physical models, it's more about physics, how the plant takes water, how it absorbs sunlight, and how it grows into a vegetation, or it produces fruit, vegetable, and other things, right? So it is a very clear understanding of how the plant actually grows using all this energy, and modeling this is science based, and it needs a lot of inputs to even attain the entire the entire process, right? And it's pretty complex, because a lot of these variables, or the assumptions, are not easily available. And when the other type of modeling is empirical or statistical fit, so you have a ground observed information and you have a measured information. You try to correlate between these two events and bring a event. So these two has its own trade-offs, right? And this empirical might work for a given region. Probably if you go to new region, it completely misses out. Where physical model will work for the other region, but it's very difficult to get those parameters for those region and other things, right? So what we generally do in the science community is like combine both. Like we try to have the underlying physics, and then try to have a empirical fit of a certain parameters which can be modeled, right? So it's a semi-physical model is what we generally prefer to go ahead. So one such model is the irrigation or and water stress modeling, right? And everyone would be aware of evapotranspiration, transpiration in general. So in schools, we would have seen you put some leaves in a plastic bag and tie it around, where you see water droplets around. So it's meaning the plant is actually releasing water to the atmosphere. So that information is very crucial. And evapotranspiration, nothing but evaporation from the soil and the transpiration from the leaves. And it's very crucial. And once we know how much evapotranspiration is having in within a field, we can actually give the information on how much water to be added. So the irrigation part is mostly like added to that, right? And then we have the soil moisture from SAR. SAR can actually measure how much water is in the soil. So that information is also important. And then we have a water balance model, which is kind of a bank balance kind of thing. How much, like you consider your farm as a bank, and then you have money, which is water. So how much water is being put? Water can come through what irrigation, it can come through rainfall, right? And water, how the water leaves out, like it leaves out either by evapotranspiration, as I mentioned, the plant transpires, right? And the evaporation from the soil, and also maybe some drainage or water can go through percolation, right? So it can go below. So once this information is there, we can actually give a recommendation saying that how much to water and when to water. So these two information are key. Usually farmers irrigate using guesswork. Like they see, or they feel like, okay, today the soil looks dry, so let me irrigate. Maybe it's not even required. And also there is a possibility of using the forecast data, seeing that there might be a rainfall in say upcoming days, and we need not irrigate. Actually, we can actually give a half irrigation and then wait for the rainfall to come in, right? So we don't need to excess irrigate. And irrigation in India, it's kind of free per se, because government is subsidizing the electricity and also water. No one cares about how much water you are fetching, but in certain countries you can see you are billed for the water you remove from the soil and also the electricity as well, right? So when there is a transformation there, probably these models are so important there. And then the other important model is like the crop yield modeling. Everyone are interested in knowing how much my farm will yield this year, right? So and even the government agency are more like fond of knowing how much yield is coming, say how much paddy is going to come this year, so that the budget can be decided, the prices can be decided, and so on and so forth, right? And there are multiple ways to do the crop yield modeling. One of them is the biomass proxies, which is basically how much biomass or how much yield is going to come is basically determined by how healthy your vegetation. Like more healthy leaves you have, you can like absorb a lot of energy, and then more energy absorbed, the more good your production would be, right? And then by tracking the growth stages also, like from sowing, flowering, vegetative, and then harvest stage, all this can be tracked through the remote sensing data. And then some people do regression, which is like correlation between the yield and the NDVI, right? Whenever we see a good greenness, it can be correlated with the yield. And the last one is crop simulation model, where it is like it is like a digital agriculture platform where you don't actually grow a plant, but you can say I am putting a seed, I'm pouring water, so much fertilizer I am putting. So the model actually has all the physics inside it, so it will try to grow a crop in a digital platform and say this much yield can come. And we can also simulate the if it a real case, like real farm, we can actually add in the remote sensing observed to correct the trajectory, right? And then comes the crop health and stress reduction. So this is one another important space where better the health and no stress to the crop is best yield. So in ideal case, when the crop is having no stress at all throughout the season, and it produces the best yield compared to the one which is stressed. And the crop health and stress are like two important features that needs to be monitored. And like I said, the near infrared part of the spectrum actually has more key information about the plant. So one information which is called red edge, which actually detects the chlorophyll decline. So it is not chlorophyll decline is not very visible in to the eyes, but whenever there is a nutrient loss or disease or something, right? So chlorophyll decline will start, but before it's visible outside, the satellite can actually sense this information and say there is a stress going on in your area. And then disease and pest signature. So you get to correlate with, like, each disease will have a different types of behavior on the plant, and that can be captured by the spectral information, the information, the band information in the satellite. And then there is thermal stress, where generally when the plants are water stressed, right? Like it closes the stomata to stop water from evaporating, so or transpiring. So when this happens, the temperature actually rises, and this information is captured as a thermal information, and the thermal band actually gives this capture this information, and you can detect this much earlier before the plant is actually drooping or it's not looking healthy, right? So you can this information, and by combining all these information, right, and this all this information can be measured using satellite on every pass, and then that information can help in making decisions what to do, and when to react, or how to act for the given condition. Then we move on to the modeling part, which is the AI, modeling in the AI part, where we let the machine understand the data and try to find patterns within the data, right? And not these two models are not competing, but they are best when used together. Like we'll have to see how can we use both together to achieve the best possible solution for the agriculture. So first off, we will start with the land use land cover classification, where this is mostly used for a government agency or agri agencies, where they would like to know how much agri land is actually in your region. So usually in the early days, people, they used to survey and they used to have a record saying so much agri could be possible in the given region. But right now we have all this satellite images, which is measuring every part of the world, and you can generate classification maps here. So here, actually, I've chosen a region which is your college. Basically, your college is somewhere here. This RMKCET is somewhere here, and you can see the classification map where I can see a few grounds probably, and then the yellow represents grassland. So there is plenty of grass in your ground possibly, and there is built up. The red one signifies the built up where college buildings are there, and then this I see that pretty much the whole area is covered with cropland. There is a lot of cropland around your college, right? So that is visible in this particular image. So how do we do this? Basically, we there are two ways to go about it. One is the pixel based, to analyze each pixel across time, across index, and say, can this be a cropland? Can this be a tree? Everything has a distinct character, and that character can be categorized as cropland, or is it a built up? Is it a water body or something like that, right? And the other, it sometimes is noisy, but the other way about to go about is use object based or the spatial based deep learning method, where the surrounding spatial information is also incorporated to decide whether this particular could be a cropland or waterland, right? So, and then next we move on to crop identification. Here's one region in northern part of India where mostly this is in the Rabi season, where mostly sugarcane and wheat are grown. And this is taken from one of my ex-colleagues' literature. And basically, the region is covered with paddy and sorry, wheat and sugarcane, and we are able to see that smaller yellow patches, which is like barren land there, and then this green and I would say some pinkish shade, which is the sugarcane and the wheat respectively. So how do we do this? This is slightly complicated than the previous problem of LULC, where we only categorize whether it's a cropland or not. And in this case, we see there is a cropland. The signature looks like a crop, and for example, like two crops might look alike, like probably a paddy and a wheat and a cotton might look alike, and over the time, the signature all if the cropping, sowing and harvest is also in the similar window, it is difficult to distinguish, but the spectral information, right? So it will be slightly varying between these two crop, and that signatures are it's very difficult for a human eye or human to tell the reason if this information is here, then decide this or that. So that is when we rely on the machine learning models, where we give all this information to the um, uh, models, deep learning models, and then we annotate all this data based on ground surveys, and then the model actually understands the pattern and um, uh, try to convert these information into a crop identification part, right? So. And then comes the field boundary delineation. So, so far we have seen this crop health, yield, and irrigation, all this. And also we have seen the other part where we have the crop identified and all this, right? So, for any analysis to be done or any uh, recommendation to be given, first is we need to know what is the farmer's plot area. So one way is to do is to digitize the farmland, right? You draw you use GPS to draw a boundary, and then you know where your farm is. But in for a country like India, where there is like a lot of farm, like 146 million, so it's difficult for everyone to go and do, and most of them are not even aware. The first way is to, like, the farmer can maybe capture their lat long and give us, but drawing a boundary for every farmer is difficult. And then this field delineation is a, solution for that, where you literally digitize every farms in the world, and then or in India, and then you try to. But the major challenge is, you see, there are a lot of, like, this region is not India, it's in Ukraine, but the farms are even smaller, or random boundaries you can see in Indian condition. The boundaries are not very clear, and we are supposed to delineate that, so that the information, probably the crops are also different when the farm boundaries are very narrow, right? So um, it's a challenging problem altogether, but that is need of the hour. Like, we are supposed to give the analytics or information, or to each of the farm, and how good it is performing, and all, for which this farm boundary is more important. And how do we do? There are multiple models that can do it, and we mainly we rely on the segmentation model. There are a lot of computer vision model. People might have been aware of this SAM, which is Facebook's model, the Meta's model, and there is the other model called YOLO, which is computer. Both are computer vision based models. And then there are certain geospatial database model, generic model, which can do all this job. So a lot of research is going on in this particular domain to do field delineation, right? And in India, the challenge is known that the plots are small, and it's very irregular in shape, and the boundaries are very narrow. So it's very difficult to make edges on these, and that's a problem people are trying to solve these days. So, so there is another challenge, which is data challenge. So all these machine learning model requires data, and even in the data part, we see, as again, the farm size are small, and people sometimes follow intercropping, like they mix two crops in the same field, and the labels which we have are very scarce. And in Indian condition, it's very the crop labels or ground truth labels are very labor expensive, because you have to digitize a lot of parts, and the ground truth collection has to be done in field surveys, uh, which is quite expensive as well. So these are data challenges, which the data actually goes through our models, and these models actually try to predict whatever models we have discussed, right? And then, so one such example, how do we use this information is, like, we have a large area, we try to identify the agricultural lands, and then we try to classify what crops are growing, and then aggregate for a given district, saying that the particular crop is growing so much, and then we can compare this against the historical numbers, acreages, right? And then see how this is standing, and then we can actually publish this as what crop is growing and how much acreage split is there in this region, right? And then the interesting part is the frontiers, which is like people are nowadays using drones and agents that talk back, right? Um, uh, it's not from far-fetched from reality, but it is something that is actually happening these days. So drones are capable of flying over your field, and it can look beyond your satellite. Satellite has a limitation of how much information it can capture for a field, right? Your field might have 1 hectare, probably there is only 10 data points you get from the satellite. But in drone, you can have a sub-meter precision where each plant can be mapped and each plant's health can be tracked. And when drones are deployed along with multispectral and thermal payloads, right? They can do much better than satellites. But the only challenge here is the area coverage, right? Your satellite covers the entire region in a single day, but your drone can't cover so much region. It can cover only a small portion. And then people nowadays are using this variable rate spraying of drone, like instead of applying like suppose your farm is affected in one area, instead of applying pesticide or fertilizer to entire region, you know where the pockets are, where your plant is not performing well, or you know where the disease is spreading. So you can spray in those regions so that you can save on the fertilizer, pesticides, and it helps in reducing the soil health, maintaining the soil health basically. And it can also be used as a ground truth collector, like instead of manually annotating this, drones can actually do a clear cut distinction between all the croplands and give a proper boundary so that it can be further used to train our satellite images. So the other part is the agents, AI agents. So right now people might be using all this Claude, Gemini, and whatnot, like ChatGPT, right? So people generally go there, ask some random question, it tries to answer. Even those answer might not be very accurate, because you the problem, you define the problem, the answer might be as good as that. So in the context of agriculture also, like how do we leverage this large language models for like a farmer to actually use it at the end, right? So we have our data layers where we have crop information, irrigation health, um, uh, and even how much yield this might produce. And we can have a weather forecast and rainfall history. And we have all these models which is doing all this effort, right? And these data can be fed to the AI agents. The AI agent is nothing but like I can make a agronomist sit and analyze the data and say how could this plot perform based on this data. Probably he might take a day of time and then analyze. Maybe if I give it to AI agent, probably it does it within a minute or so, right? It can analyze all the data and correlate based on the knowledge it has, and as the LLMs keeps progressing, the knowledge of these LLMs are going to be high, and these agents, AI agents, you say, right? They help in giving information. That too in the language that too in the language that people can understand. It can answer, like right now most of the LLMs support tons of languages, Indian languages also. So the next is like let's imagine a bit more, like how would it be when suppose there is a robot or something that can do every job a farmer is doing. So that is not far fetched from future, but that people are still using it in labs on certain experiments are happening at a high cash crops, right? Like strawberry and all, people use autonomous robots to do this. So, in farm robots, what it can do is like it can actually go look at the plot. If there is weeds, it can, instead of using pesticides or not pesticides, I would say, like there is herbicides where to kill the weeds and all, right? These robots use laser to just kill the weeds, and then it keeps on going. It sees the difference between, it identifies a strawberry plant from a weed, and then it kills the weed and go on. And then people use farm robots to harvest, like to see which part. Like strawberry is generally picking, and it's it requires tremendous effort. Like you have to go, you have to see which one is ripe, and you pick that. If you pick a unripe fruit, it's a waste. Like you'll have to dump it in the garbage. And these things can be automated using robot. And we can also have like right now we can see there is a lot of AR glass or the Meta glasses which we see in the market, right? So it can long back, farmer having a smartphone was thought as like it's not possible. Farmer can't have access to internet and stuff like that. But now you see almost every farmer has a smartphone, and he can get a lot of information that. So getting a VR glass might be looking in the same way, but it's not far-fetched. Like you maybe in next 5-10 years, a farmer might be able to afford the prices of the Meta glass might come down, and then they might be having all these Meta glasses where he can literally interact with the Meta glasses. Meta glasses actually captures the leaves. He can take photographs, and he can share to the agents, and then agents read, and he can ask some random questions like why this plant is looking bad. Do you see any problems? Probably the AI agents can answer back saying that probably there is this disease or this effect, or your maybe even your plant looks normal, it's all good, something like that, right? So so we see there is a lot of labor shortage also in even in India, because people are slightly moving from agriculture to organized sector jobs, right? And there will be labor shortage, and these things might come handy to do to do a lot of work in a given short frame. So what we expect is a closed loop system where we have deployed a lot of sensors um, which actually measures the agriculture fields, be it sensors, drones, cameras, or whatever. And then we pass on those information to AI agents or models where it aggregates all this information, try to analyze, find a correlation, and then give a recommendation that we can act upon. The act upon recommendation could be as simple as turning on the irrigation pump, or cutting off the irrigation pump, whatever it may be, right? So, or even a robot which can go inside, do de-weeding, and it can do harvesting, right? So this, if the whole cycle is automated, then we don't really need to go and do all this agriculture practices. The drones or the whole autonomous system does the entire cropping for us. So, what are all the opportunities in this field? So, there is plenty of research opportunities, I would say. Like, you can, there are a lot of open problems and challenging problems. And as the tech evolves, there is a lot of new avenues to investigate. And there was no concept of agents at least 2-3 years back. And now you see agents has become a core context on agriculture also. So people are using all different technologies in agriculture, and the research area is wide open. And in startup point of view, you anyone can build an advisory app. They can do a drone service, and fintech and agri with all this information, right? And then with the growing agronomy related tech companies, you can see there is a lot of geospatial AI and ML engineers with remote sensing and knowledge, right? They are also growing fast, and Yeah, and anyone can jump in and try out different ideas, and you can start today, even seeing the images. How does it look, and um, how can it be leveraged for the next agricultural solution, probably, right? So with this, I come to end of my talk, and feel free to ask any questions or anything, if any. I'll be happy to answer those.
Thank you. It was a wonderful session. So, on behalf of RMK Group of Institutions, I sincerely thank Dr. Deepak for delivering an informative and insightful session on remote sensing AI and next frontier of precision agriculture in India. So, the session clearly explained the major challenges that has been faced by the Indian agriculture, and he demonstrated how the remote sensing and AI can support the precision farming. So he started from a very basic level, like for a layman, like what is the importance of farming, and what is the necessity of doing getting a support from a technical team for doing an precision farming, right? So the discussion entirely covered with that optical and radar remote sensing, and he told about the true color and false color imaging, and he talked about the vegetation indices and even the cloud related information and the importance of SAR during the monsoon season. So for those who are very beginning to this agrotech mm, perspective, it is very informative. The explanation that healthy vegetation, it appears predominantly red than in the false color imagery was it was interesting to listen to. The overview of satellite platforms such as Sentinel-1, 2, and Landsat was highly useful for the students and researchers, I hope. Those who are will be interested in start their research or their BE project in agritech or real-time agricultural data. Thank you for that. And the session also provided the valuable insights into the physical model and the empirical model and the hybrid approaches. The explanation about the transpiration and the proper water requirements and water balance modeling and water stress modeling was very informative. The analogy of treating water like money in a banking system made the water balance model concept simple and memorable. Anyone who is into this, right, they can do a simple kind of project and they can extend it to a bigger research. The discussion on crop yield monitoring or crop health monitoring, stress detection, crop identification and classification, and field delineation effectively demonstrated like how satellite imagery and AI can identify the crop types, distinguish between the individual agricultural fields, and monitor their condition and support field level decision making. The explanation of land cover classification was also highly engaging. Seeing the classification of our own college surroundings, it was very good to see, like including the crop areas, wetlands, and water bodies, made the session more reliable and interesting. The explanation of drone-based agricultural monitoring further highlighted like how the people who are very interested in autonomous robots can pick up this as one of the application problem, and they can pursue their final year project or their research. And to add, like everyone are using this chat GPT or Claude or Gemini AI, and he has given a insightful word of how agentic AI will be used for this precision agriculture. So this entire session was very informative, and thank you, sir, for sharing your valuable knowledge and practical examples and useful data sets and inspiring insights that you have shared with us. Thank you so much. And we also express our sincere gratitude to the management and the administrative heads for providing this valuable platform through the generic talk series, which regularly enhances the knowledge of all stakeholders. Either it is going to be for the B students or the postgraduates and researchers, faculty, as well as the parents. We thank Dr. Regin Pal, faculty from Department of Computer Science and Engineering, and Dr. S. Keetana from our own department for their support in moderating and successfully conducting this event. Thank you, Regin sir. Thank you, Keetana, for being with us. And finally, we thank all the stakeholders who joined on this Sunday morning and benefited from this session. Thank you. Thank you so much.
Thank you for the opportunity, ma'am. Yeah, thanks.